Okay, another assumption we must check is for normality. We need to check this to be able to make inferences from our sample data to our population data. So there are a few tests that we can carry out. We can visualize the residuals using a histogram and a QQ plot. We can then run tests including the Shapiro-Wilk test and the Anderson-Darling normality test. We can use the Shapiro-Wilk test with a sample size of up to 5,000. So as we have over 6,000 observations, we will use the Anderson-Darling test. So for the histogram, we will just use the basic histogram function. We plot the original model's residuals and check for the normal distribution. In this case, we do not have symmetry. Now, if you remember the original model from part 1, when we checked the residuals, we did not have symmetrical values. So this is a visualization of these values. Another visualization is the QQ plot, where we use the QQ norm argument and the QQ line argument. With the residuals, the QQ line will add a 45-degree line on the plot, and we want to illustrate how many points fall off this line from the model's residuals to the theoretical values of that line, which represent the normal distribution. And in this case, we can see that the upper values have many data points that are off that line. So it could be suggested that our model may not be more normally distributed. So let's run that Anderson-Darling test. To use the Anderson-Darling test, we load the NORTest package to use the ad.test function. We then place the model residuals in the brackets. So our alternative hypothesis here is that the model residuals are not normally distributed in our model. So if we run that code and we check that p-value, it's under 0.05. So we reject the null hypothesis and conclude that our model residuals are not normally distributed. There are a few remedies to this. We could use a generalized linear model that relaxes the assumption of normality. But here we will use the Box-Cox transformation test. This tests out if we should transform our outcome variable and to which power to transform it to. So to run this test, we need to make sure we have no negative or zero cases. So as we do have data zones with no alcohol-related hospital stays, we need to add an additional 1 to the value. We then create an object, let's just call it PT. We then use the power transformation argument, and then we indicate our outcome variable in the brackets. We then use the summary with the newly created object in the brackets. So as I'm using R Markdown, there are 3 different outputs here. The most important is the first output and the last output. So the last output has our p-value, which is under the 0.05. This means that we should make the transformation. If we look at the first output, under estimated power, reveals how to transform the outcome variable. So here it tells us that it should be raised to the power of 0.2223. So we need to create a new variable to rerun the model. So here we create a new outcome variable. We place the original in the brackets. Then we specify that we want to raise to the power of 0.2223. So when we rerun the multiple linear regression with the newly transformed outcome variable, we then check if our predictors are still significant, which in this case they are. We can also see that the estimates have changed dramatically. However, there is no clear way to interpret these results. But if you look at the difference of residuals now, the local median is near zero, and there's more symmetry between minimum and maximum residual and the first and third quartile. So the last assumption we will check is for multicollinearity. This can occur if a predictor is a function in another one of the predictors, meaning that they may have a high correlation between them. So to check for this, we need to create a new data frame of the predictors. We create a new name for the global environment. Let's just call it SIMD2. We then use the data frame argument, and then we include our predictor variables. For the dummy urban, we need to use the numerical version. So let's run that code and look at the first 6 rows. Looking good. Okay, then we create a correlation matrix of the predictors that will reveal the correlations between each predictor. So we use the core function, we use the new data frame created above, and we use the use equals complete obs. This just tells R to exclude missing values. So when we look at the output, we are looking for any values to be near 0.8. So here we can see we have a high correlation between no qualifications and income rate and the depressed variable. So we may have multicollinearity. A test we can run to give a clearer picture is the VIF test, which is short for Variance Inflation Factor Test. So we use the VIF argument and place the original model in the brackets. If we have any values equal to or greater than 10, then we have multicollinearity. So here we see that the highest value is 5.6. We therefore have no multicollinearity. If we did have a value over 10, we would need to remove the variable from the original model and start again. Hopefully this tutorial has got you familiar with how important it is to check those assumptions of multiple linear regression, how to check them, and what to do if we violate them. So happy coding, Q-steppers, and remember to subscribe to our social media channels, and thank you for watching.